So in the last class, I discussed up to this topic, where actually I showed you finally that photodiodes can be operated in three quadrants: first quadrant, third quadrant, fourth quadrant. Third quadrant is used I told you that to use the photodiode as a photodetector, and the fourth quadrant operation is used to use the photodiode as a solar cell or battery, right? That's the thing I discussed in the last class. So today we'll look into solar cell and photodetector more uh, in more detail. So article 8.1.2 solar cells. Now in the last section I told you that solar cells, photodiodes can be used in the fourth quadrant, can be operated in the fourth quadrant to deliver power to the external circuit, right? So since power can be delivered to an external circuit by an illuminated junction, it is possible to convert solar energy into electrical energy. So actually what was happening here, since this is a illuminated junction, you just connect these two terminals through a resistor, current will flow because of illumination, and this current is generated by optical means, right? This current originates because of the optically generated carrier. So here this current will deliver power here, I square R. So effectively what you are doing is here the optical power, optical energy is being converted into electrical energy. So solar sunlight can be used to generate electrical energy. So that is the photodiode which converts sunlight or solar energy into electrical energy. That is the solar cell, right? Now, in designing solar cell, we have two problems. When you try to use photodiode as solar cells, two problems are there, which I have marked with two different colors. The voltage is restricted to values less than the contact potential, which in turn is generally less than the band gap voltage Eg by Q. For silicon, the voltage VOC is less than 1 volt. So remember, in the last section, I showed you the expression of VOC, and I told you that VOC upper limit is VO, the contact potential, this VOC. The upper limit of VOC is this contact potential VO. So VOC can be maximum VO, contact potential, and VO, the QVO actually, this is less than the band gap EG, because you can see when you form the PN junction, the Fermi levels are being aligned. Because of that, this shift is there. The difference between the conduction band of N side and P side is determined by the shift of the energy bands in order to align the Fermi levels. And this shift, amount of shift, obviously you can see that it's less than this EG. So this QV0 is less than EG. So V0 has to be less than EG by Q. Okay, so that means VOC also is less than Eg by Q. So for silicon, Eg, the forbidden gap or band gap is around 1.12 electron volts. So you can understand VOC has to be, or VO has to be less than that voltage, right? So that is a limitation. The voltage is restricted to values less than the contact potential VO, which in turn is generally less than the band gap voltage Eg by Q. For silicon, this voltage VOC is less than about 1 volt. You know that is around 0.7 volt. Now, this is one problem. The amount of voltage you get from a solar cell is small, and the maximum value is contact potential VO. And the second problem is, there is another problem. Typically, IOP is in the range of 10 to 100 milliampere. So IOP is the optical current, optically generated current, that is in the range of this milliampere. So this is a small current for a junction with an area of about 1 centimeter square. 1 centimeter square is actually a very large area, I would say. So even for a large photodiode, or I should say thick photodiode, the current obtained is not large, it's a small current. So these are the two problems of using photodiode as solar cell, but there is a solution. Okay. Solution is you can use multiple solar cells, combination of solar cells or array of solar cells or photodiodes, so that the voltage and current can be increased. Okay. However, in if many such devices are used, the resulting power can be significant. In fact, arrays of PN junction solar cells are currently used to supply electrical power. So, by series parallel combination of multiple solar cells, you can increase both the voltage and the current. Okay, if you connect the several solar cells in series, then the total voltage obtained from the series combination will be larger, right? And also such branches, if you connect them in parallel, then the total current obtained from all those solar cells will also be large. Okay, so series parallel combination, by using those, you can increase both voltage and current. So that's why it said that the array of PN junction, multiple PN junctions, can be used to supply substantial amount of electrical power. Okay, so this is the solution. So there are two problems. There is a solution. Now there are some design considerations of solar cell. There are actually 6 design considerations which I have shown here using alternate color. So yellow, blue. One design considerations, second, third, fourth, fifth, and sixth. 6 design consideration, and there are also some images. This is one figure, and this is another figure for design consideration. So let's see what are the design considerations. To utilize a maximum amount of available optical energy, it is necessary to design a solar cell with a large area junction located near the surface of the device, figure 8.5. So this figure actually, this is a cross-sectional view of a solar cell, which is basically a PN junction photodiode, you remember. And this is the top view. So top view is you are looking from this side. Okay, this is the top view. You are looking from this side. So you can see here there is N type material, there is P type material, there is contacts, and there are some other layers, and light is coming from this side. So obviously you can understand light will penetrate this surface, will go into the uh, depletion layer or close to the depletion layer of this PN junction, and will generate optically generated carriers, excess carriers, and those carriers will take part in the current conduction, which gives actually the IOP, optically generated current, from N to P, right? So obviously you can understand, if you can increase the surface area, the top area, that means this area, more is the area, more is the light incident or available to the junction. Okay, incident on the junction. So large area PN junction, more is the light available. So of course you can understand more is the number of carriers generated, optically generated carriers. So obviously if more is the number of carriers generated, then current will also be more, right? So uh, that's what it is mentioned here. To utilize a maximum amount of available optical energy, it is necessary to design a solar cell with a large area junction located near the surface of the device. Why near the surface? The junction should be near the close to the surface, because you can see light has to penetrate this region to go to the depletion layer or near the depletion layer. Remember, the carriers which are generated within the depletion layer or near the depletion layer, those are useful. Those take part in the current conduction, optically generated current conduction. So this light has to penetrate up to that depth. Okay, so that's why the PN junction has to be close to the surface. It is deep into the silicon, then what will happen? This light may not, or many photons will get absorbed in the path. They will not reach the depletion layer at the junction. So the number of carriers which are optically generated will become smaller. So that will reduce the optically generated current, IOP. So that's why the junction has to be close to the surface. So large area junction and also junction close to the surface. That is one design consideration. Understood? Hmm? Hello, are
Yes,
you
sir.
here?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
The second design consideration, the surface is coated with appropriate materials to reduce reflection and to decrease surface recombination. So what is that? Since light is coming from this side, uh, if there is reflection on the surface, so what happens? Reflection means the incoming light, a portion of the incoming light is going back to the air or going back to the environment, right? So those photons which are going back, light which is going back, those photons will not penetrate into the semiconductor, into the junction, and they will not take part in carrier generation, right? So you have to reduce reflection. How can you reduce reflection? There are special materials called anti-reflective materials. You can use a coating of that kind of material on the surface so that the reflection is reduced. So most of the incoming photons will get through, will go through the coating and will be absorbed in the underlying material, which is the PN junction, right? Yes. Hello. So that is the job of anti-reflective coating. And also you have to have some kind of passivation layer. Passivation layer is required. Why? Because this surface, you can see surface of the N region, this surface is equivalent to a crystal defect. I have already told that in previous classes. Surface is viewed or can be viewed as a crystal defect because at the surface periodicity of the crystal is violated. Okay, so whenever there are defects, what happens in the energy band diagram? Anyone remembers? Additional energy states, trap states are created within the forbidden gap, right? So when trap states are created, what happens when an electron absorbs light and is trying to go to conduction band from valence band, it may get trapped in the trap level, in the trap states, and from the trap state it may even come back to the valence band. Instead of going to conduction band, it may come back to the valence band. So those trap states actually will reduce the number of carriers generated. So that will also reduce the photo generated current, IOP. So remember, we our objective is to maximize V voltage obtained from the solar cell terminal and also the current obtainable from the solar cells. Okay, so anything that reduces the voltage or current that is bad, we will consider that something is not desirable. So uh, this kind of surface defects can be reduced to some extent by using special layers of material which are called passivation layers. Okay, so passivation layers can be used to reduce this kind of recombination at the surface, which the surface recombination, as I told you, will reduce the number of carriers generated. Okay, so passivation layer is also a special type of layer which maybe you have to use. So the surface is coated with appropriate materials to reduce reflection and to decrease surface recombination. Surface recombination happens because of surface defects. So these two design considerations should be clear, right? Then third design consideration, junction depth D must be less than LP in the N material to allow holes generated near the surface to diffuse to the junction before they recombine. So remember, these lights come and they generate carriers here in the depletion layer or near the depletion layer, and holes from N type material, they can diffuse to the depletion layer and can go to P side. That constitutes a optically generated current from N to P. And also electrons created in the P layer close to the junction, they may diffuse to the depletion layer and can go to the N side, constituting another current component which is also directed from N to P. Electrons going from P to N, so current is directed from N to P. So for hole diffusion in the N material, the holes has to be created close to the junction, as I have showed you in the first class in on this uh, optoelectronic devices. This here, that there are three regions where the carriers which are generated are useful. One region is this W, one region is within one diffusion length, electron diffusion length in the P side, and on the N side within one diffusion whole diffusion length at the N side. So these electron holes which are generated within one diffusion length of the depletion layer, sorry, depletion layer edge, those holes are useful. So if N layer is too thick, if N layer is too thick, the holes which are generated far from that depletion layer edge, they cannot diffuse to the depletion layer. They will recombine before they diffuse to the depletion layer. So that's why the thickness of the N layer, which is this D, has to be less than the electron diffusion, sorry, hole diffusion length. Okay, so that the holes which are generated here can go to the depletion layer here. Similarly, for p-type material, in the p region, similarly, the thickness of the p region must be such that the electrons generated in this region can diffuse to the junction before recombination takes place. So here also, electrons generated close to the junction, they can diffuse here and take part in the current. So electrons which are generated far from here, they may not diffuse and will not contribute to the current. So that is another consideration for p-type also. But for p-type, there are additional consideration. The thickness of p-type material also has another additional consideration, which is the optical penetration depth. That means these photons, they can penetrate up to certain depths. Uh, when they are penetrating this semiconductor, they are getting absorbed. If you remember, so when they are getting absorbed, if they are getting absorbed, you can understand, far from the surface, a very small number of photons can reach. Okay, before they come here, they will get absorbed here. So that is another consideration. Optical penetration depth, thickness of the p layer has to be adjusted in a way considering this optical penetration depth and considering the electron diffusion length here, uh, so that the electrons generated here can be maximized close to the junction and they can diffuse to the junction depletion layer. So this is the third design consideration. Junction depth D must be less than LP in the N material to allow holes generated near the surface to diffuse to the junction before they recombine. Similarly, the thickness of the P region must be such that the electrons generated in this region can diffuse to the junction before recombination takes place. This requirement implies a proper match between the electron diffusion length Ln, the thickness of the P region, and the mean optical penetration depth. Mean means average optical penetration depth. How, on average, how far and the light can penetrate into the material. So that is third. Now fourth design consideration is it is desirable to have a large contact potential VO to obtain a large photovoltaic. So VOC, remember VOC is the voltage across the solar cell with open circuit. Now uh, our objective, I told you, to increase this voltage obtainable from the solar cell terminals or across the PN junction. So one way to get that is to increase VO, the contact potential, since contact potential VO is the maximum limit of VOC. So if you increase VO, VOC will increase. So how can you increase VO? Anyone remembers? Hmm? Can anyone tell me how VO can be increased? The equation of VO contains the equation of VO is KT by Q ln of NAND by NI square, right? So obviously NAND, the doping concentration. If you increase the doping concentrations of the N side and P side, VO will increase. But there is a problem. So therefore, heavy doping is indicated on the. There is a problem. So that's on the other side. On the other hand, if you increase doping, the carrier concentration of N side and P side will increase. So as the carrier concentration increases, the recombination rate will increase. So recombination rate increases means the recombination lifetime will be small. Okay, a smaller recombination lifetime is not desirable. Here we want long lifetime, large recombination lifetime. Why? Because we want the carriers to survive recombination before they reach the depletion layer. They should not, the carrier should not recombine when they are going to the diffusion layer. They should reach the diffusion, sorry, not diffusion, sorry, depletion layer. They should reach the depletion layer. Okay, if the carriers recombine before they reach the depletion layer, then that carrier is useless. So that's why we want long lifetime. So this implies that the doping should not be very high. Okay, so there is a contradictory requirement here. Large V requires heavy doping, but long lifetime requires uh, light doping. So there has to be a compromise here. As the designer of a solar cell, you have to choose a suitable value so that both VO and lifetime, these contact potential and lifetime, both are at acceptable levels. So this is the fourth design consideration. The fifth design consideration is regarding the contact resistance. It is important that the series resistance of the device is very small so that the power is not lost to heat due to ohmic losses in the device itself. So if there is a uh, I square R loss in contacts, then uh, the power obtainable from the solar cell gets reduced. Remember, each solar cell can deliver very small amount of current. So if the power delivered by a solar cell is already not very high, it's small, I square R. R is the external resistance. So obviously you can understand if a portion of that obtainable power is lost as a ohmic loss, then the power delivered to the external circuit will get reduced. So that is a loss. We have to minimize that loss. So a series resistance of only a few ohms can seriously reduce the output power of a solar cell. So how can we reduce the series resistance of the solar cell? Remember this PN junction, this solar cell has to be connected to a external circuit, to a register, right? Like this, which has been shown in the last class. Like this PN junction has to be connected to external. So this is the register. So this PN junction delivers power to this load. This is the
অ্যাটেন্ডেন্স কটার দিকে নিতে পারে কেউ কি ঢুইকা আসুস ভিতরে
এদিকে so this is delivering power to the external register. This is the load. Okay, and remember this current is actually independent of this R, right? Sorry, yeah, independent of that. This depends on the optical generation of carriers. So if in the contact, this N type has to be N side has to be contacted, has to be connected to this external circuit. Also, this P side has to be connected to the external circuit, right? So that contacts, if they contain some resistance, then it will be a problem. There will be I square R loss. Now P side we do not have much problem because since light is not coming from this side, light is coming from this side, N side. Uh, you can use the whole P side as the contact. So the contact resistance of the P side will be small. It is negligible. The problem is the N side, contact on the N side, because if you put contact, light cannot penetrate the metallic contact, right? These are metal semiconductor junctions, these contacts, ohmic contacts. So you have to provide a space for light to penetrate the surface. So how can you make contact? You have to uh, provide area for light penetration, and also you have to provide contacts for collection of the current. If you put only a few contacts which are far apart, you can understand the current which, or the carriers which are generated here. Those carriers has to travel long distance to go to the contacts, and so that will increase the resistance of the contacts here. Contact resistance will increase, so I square R loss will increase. So you have to use frequent contacts, many contacts, but again you have to let the light penetrate the surface, go through the surface into the material, semiconductor material. So one way is to do that by using multiple thin contacts which are connected to a large thick contact. So these multiple thin contacts, they are called contact fingers. So since there are multiple contacts, the carriers can be collected from all over the junction by these thin contacts, but still there are sufficient area for light to penetrate. So this kind of contact arrangement is required on the N side. On the P side, since light is not coming from the P side, the whole surface can be used, can be coated with metal to make the contact. So that is the fifth consideration. Since the area is large, the resistance of the P-type body of the device can be made small. As I told you, uh, P side, we do not have any problem with contact. However, contacts to the thin end region requires a special design. If this region is contacted on the edge, current must flow along the thin end region to the contact, resulting in a large series resistance. So to prevent this effect, the contact can be distributed over the end surface by providing small contact fingers, as in figure 8.5b. So this is figure 8.5b. This is the top view. This is the cross-sectional view, and if you look from this side, this is the top view. So these contacts are these contacts. Okay. These narrow contacts serve to reduce the series resistance without interfering appreciably with the incoming light. Okay, so since these contacts are narrow, still light can penetrate the surface through this region between the contacts. So fifth design consideration, then last one, sixth design consideration. Actually, this is about the figure of merit. Figure of merit is something which denotes a performance issue of a device, how good or how bad the device is in terms of a specific performance. So this is the IV characteristics of a solar cell And this actually comes from the fourth quadrant of the IV characteristics of the photodiode. This part is that part, this fourth quadrant part. Here current is negative since it is going from N to P. But if we consider this as a battery, then we can think that the current is positive. When we are considering this as a PN junction, definitely the current is negative, it's going from N to P. But if we consider this as a battery, we can consider this same IR as positive current. So we can revert this, we can invert this or flip this part. Uh, so the negative current will become positive current and we get that curve. That curve I just showed you. এই গেল। I don't know. This curve. So you can see when the solar cell is open circuited, there is no connection between P side and N side. We get open circuit voltage VOC, but current is 0. And when we short circuit the terminals, we get ISC, but voltage is 0. So along this axis, voltage axis, VOC is the maximum attainable voltage from a solar cell, and along this axis, ISC is the maximum attainable current from a solar cell. But both are useless because when circuit is open, current is 0, no power can be delivered. You are getting larger voltage I should say, but current is 0. So the power delivered to the external circuit, there is no external circuit connected, is 0. And when the circuit is shorted, that means there is no external load. RL is 0. So in this case also no power can be obtained from the device. No power can be delivered from the device to the external circuit. So in order to get useful power, actually you have to operate within this limit, not VSOC, not ISC, but any place other than these 2 points. You can see there is some value of voltage and some value of current. Say for example, if you choose this point, if the solar cell or photodiode is operated on this point, at this point of the IV characteristics, so corresponding voltage is this and corresponding current is this. So the power delivered will be this V into this I, right? So that is effectively the area under this rectangle, right? So let's this figure 8.6 shows the fourth quadrant portion of the solar cell characteristics with IR plotted upward for the convenience of illustration. So as I told you, this IR was negative in the diode characteristics, but in solar cell characteristic it has been considered as positive. The open circuit voltage VOC and the short circuit current ISC are determined for a given light level by the cell properties. And I have already talked about VOC ISC in the last class. The maximum power delivered to a load by this solar cell occur when the product V into IR is maximum. So you can say see that at different points on this curve, VIR will be different. V into I will be different. So V into I, if you remember, is the power. So at some point, V into I will be maximum. That means the area under the rectangle will be maximum. That point is the maximum power point. So in this case, say this point is the maximum power point, where the area under this rectangle, that means this V into this I is maximum. So the V and I corresponding to this maximum power point is Vm and Im. Remember, Vm is not the maximum voltage, Im is not the maximum power, sorry, maximum current, but Vm, Im, they corresponds to maximum power. Okay, their product is maximum for this point. So that's what it is mentioned. The maximum power delivered to a load by this solar cell occurs when the product V into IR, this V into this IR is maximum. Calling these values of voltage and current as Vm and Im, that means this and this, we can see that the maximum delivered power illustrated by the shaded rectangle in figure 8.6, this rectangle is less than VOC ISC, VOC into ISC. VOC ISC is actually the area under this rectangle. Okay, so this power is never obtainable from a solar cell. It's not practical because when voltage is VOC, current cannot be ISC, or when current is ISC, voltage cannot be VOC. So this power is not obtainable, but this is a reference point. So any power obtainable from this uh, solar cell at different point is less than this VOC ISC. So the maximum power which is obtainable VMIM that is also excuse me smaller than VOC ISC. So this ratio VMIM by VOC ISC, this is called fill factor. This is a figure of merit for solar cell. So fill factor is you can understand always less than 1. It cannot be greater than or even equal to 1 because VMIM is always less than VOC ISC. And this is a figure of merit. That means higher is the value of fill factor, higher is the maximum power obtainable from the solar cell, so better is the solar cell. So as I told you, figure of merit denotes how good or how bad a device is in terms of performance. So in terms of power, uh, higher fill factor means better solar cell, or lower fill factor means not so good solar cell. So this is actually regarding the figure of merit, but figure of merit is also related to design considerations, since a solar cell with larger fill factor is better, is desirable. So I have also included this in the design consideration. So there are in total 6 design considerations for solar cell, and these 2 figures and this figure. So that's all about solar cell. Any question on solar cell? No question. So okay, let's move on to the next topic, photodetector. So photodetector, if you remember, photodiodes operated in third quadrant. So when the photodiode is operated in the third quadrant of its IV characteristics, the current is essentially independent of voltage and is proportional to the optical generation rate. So in the third quadrant, if you remember, reverse bias voltage is applied. So when you apply reverse bias voltage across a PN junction, what will happen to the current? Current will become this V. This is the current of equation of illuminated diode. This V is negative. So this, if it is large enough compared to KT by Q, this term becomes 0, almost 0. So effectively I equal to minus I thermal minus IOP. I thermal is IO, if you remember. So I is minus IO minus IOP. IO is very small. IO is very small. Dark current is also called dark current, reverse current without any illumination. But IOP can be very large. So you can understand that I equal to minus IO minus IOP. Minus IO can be ignored since this is very small compared to IOP. So I is equal to IOP, optical, and I optical is directly related, directly proportional to optical generation rate, G optical. Okay, so in the third quadrant operation, the current is actually dependent on optical generation rate. It does not depend on the voltage. Okay, this term vanishes in the third quadrant, reverse bias junction. So photodetectors are those which can detect the presence or variation of light. So the current depends on light intensity. It depends on optical generation rate GOP, which depends on light intensity. So you can see that that photodiode can be used as a detector of light. So that's what is mentioned. When the photodiode is operated in the third quadrant of its IV characteristics, the current is essentially independent of voltage but is proportional to the optical generation rate, GOP. So I equal to minus IO minus IOP. So this is negligible. I is IO minus IOP. IOP is proportional to GOP. Such a device provides a useful means of measuring illumination level or of converting time varying optical signals into electrical signals. This is important in optical communication where we send data through optical means. We use light to send data. So at the receiving end, there is some variation of light based on the data it's carrying. So you have to detect this variation of light to understand the data, to extract the data from the light. So if in that kind of situation, or also measuring illumination level, that is these photodetectors are useful. So there is a design issue here. The most in most optical detection application, the detector's speed of response or bandwidth is critical. For example, if the photodiode is to respond to a series of light pulses 1 nanosecond apart, the photogenerated minority carriers must diffuse to the junction and be swept across the other side in a time much less than 1 nanosecond. So, as I told you, optical communication, nowadays most of the communication are done actually using are digital communication. Analog communication is not used. So a typical type of optical signal for digital communication may look like this, where optical intensity increases and decreases corresponding to a digital signal, electrical digital signal. So this optical signal can be converted to a electrical signal, variation of current using this photodetector. When light intensity is large, current will be large since IOP is proportional to GOP. And when light intensity is low, current will be low. So this variation of light can be converted into a variation of current, provided the photodetector is sensitive. That means the, in order to detect this variation of light, remember the change of current will occur because of creation of excess carriers by this uh, light. So those minority carriers have to be created. They has to travel and go to the external circuit uh, to detect this variation of light. So though that is a time consuming process. So the detector speed is very important when light pulses are varying very fast. If the light pulses has to be this variation has to be detected precisely, then and the speed of the photodetector has to be even faster. Okay, the um, photodetector must detect this variation very quickly. Otherwise, before the detection is complete, the light pulse level will change. So it will not detect the variation of light correctly. So data will be lost in that case. So that's what it is mentioned. For example, if the photodiode is to respond to a series of light pulses 1 nanosecond apart, so this gap is 1 nanosecond, the photogenerated minority carriers must diffuse to the junction and be swept across to the other side in a time much less than 1 nanosecond. That means it has to be very fast. The carrier diffusion step in this process is time consuming and should be eliminated if possible. So the carrier diffusion step happens in those regions. Remember, there were three regions where the generated carriers are useful. One is the depletion layer, depletion region area, the first class. Uh, Here, the carriers which are generated within W, that is useful. The carriers which are generated within one diffusion length, in this case, electron diffusion length in the P side, those carriers are also useful. And the carriers which are generated within one whole diffusion length in this N region, that are also useful. But in the case of photodetectors, the carriers which are generated in these regions, in the one diffusion length from the depletion layer, with those carriers actually will take time to diffuse to the depletion layer and then to the other side. So these diffusion carriers, diffused carriers should be minimized. We should not rely, photodetector should not rely on these carriers which diffuse to the depletion layer because this diffusion process takes time. So in order to speed up the response of the photodetector, most of the carriers should be generated within this depletion region, within this W. So from that perspective, W should be large. Okay, so that the most of the incoming light, incident light, creates photogenerated carrier within the depletion layer. Okay, so that those carriers don't have to diffuse to the depletion layer, they are already within the depletion layer. So that is the thing there. The carrier's diffusion step is in this process is time consuming and should be eliminated if possible. Therefore, it is desirable that the width of the depletion region W be large enough so that the most of the photons are absorbed within W rather than the neutral N or P region. That means neutral and P regions means within that one diffusion length. When an EHP is created in the depletion region, the electric field shifts the electron to the N side and hold to the P side, which is the cause of that IOP, optically generated current. Since this carrier drift occurs in a very short time, the response of the photodiode can be quite fast. So the carriers which are generated within the depletion layer, they can shift, uh, travel very fast because of the electric field in the depletion layer. So the response of the photodetector can be fast. So obviously it is desirable to dope at least one side of the junction lightly so that W can be made large. You can dope actually both sides of the PN junction lightly or at least one side of the PN junction lightly so that you can get large W. Remember, if you dope P and N side, both side heavily, W will be small. But from this discussion, we can see that W should be large um, to generate most of the excess carriers within the W. So that's why the doping cannot be large on both sides. At least one side doping should be light. Now there are figures of two properties actually of a photodetector which are important. One is sensitivity and one is the speed of response. I already talked about speed of response, how fast the uh, photodetector can detect the variation of light, that is the speed of response. And the sensitivity, sensitivity is the fact that what is the minimum level of optical energy which can be detected by the photodetector. Okay, you can understand if the number of photons is small, the carriers generated will be small, so the current will be small. So if a photodetector can generate large amount of current even for a small number of photons, that photodetector is more sensitive. Okay, so sensitivity and speed of response, these are the two important figures of merit, you can say, for photo detector, but there has to be a compromise between these two because there are contradictory requirement for these two uh, aspects. The approximate width of for W is chosen, so the appropriate width of W is chosen as a compromise between sensitivity and speed of response. If W is wide, most of the incident photons will be absorbed in the depletion region. As I told you, if W is wide, lights are coming, most of the lights will fall on the depletion region, and so most of the carriers will be generated within the depletion region. So the device will be more sensitive. Okay. If W is wider, the device is more sensitive because the number of the photons which are incoming, which are coming, can be used more efficiently to generate useful carriers. Uh, Also, a wide W results in a small junction capacitance, thereby reducing the RC time constant of the detector circuit. Remember, this is a reverse bias PN junction. So in a reverse bias PN junction, there is junction capacitance, and then junction capacitance is epsilon A by W. So W increases, the capacitance decreases. So this is connected to a RC, a resistor, and a battery, if you remember. So in that circuit, there is associated RC time delay. R is there, and from here, junction capacitance is there. So there is a associated RC delay. So if the capacitance is small, RC delay is smaller. So that is also useful. That is also a good thing for detector circuit. So large W is good in terms of sensitivity, in terms of RC delay. But there is a problem with large W. On the other hand, W must not be so wide that the time required for drift of photogenerated carriers out of the depletion region is excessive, leading to low bandwidth. So if the carriers have to travel a long distance, then it will take too much time for the carriers to go to the external circuit. So the device response will be slow. So what is that? Say this is a PN junction, so W is wide. You want, okay, you want to make a W even wider to make the device more sensitive. So you make a PN junction like this wide. So this may be too wide for the carriers to travel to the contacts. Remember, contacts are here at this point. Travel to the contact. So that will reduce the speed of detection. Okay, so there has to be a compromise in W so that the reasonable speed and reasonable sensitivity both are obtained. So this is a design issue, or this is a compromise in design. Now, types of photodetectors or photodiodes. There are basically two types of photodetectors. One is pin photodiode, and the other is avalanche photodiode. Pin photodiode is actually P intrinsic N, and there are three layers which are sandwiched like this, PIN. So light falls on the PN junction, sorry, PIN structure. The depletion layer actually extends from somewhere within the P to somewhere within the N. So most of the depletion layer is actually covered by the I layer depletion. So if by increasing or decreasing this I layer thickness, this W depletion layer width can be changed. So pin structure is used actually to have a control over W. Okay, when you make pin structure, you adjust the width of the I layer, and accordingly W will be adjusted. So how does this work? You can understand intrinsic part. This is has higher resistivity, since the carrier concentration in the intrinsic material is smaller than P or N, so it has higher resistivity. So most of the voltage which has been applied here will appear across this high resistivity I layer. So the electric field will be across. There will be a large electric field across this W, this depletion layer. So uh, you can say, since this W is large and W is controllable, So the sensitivity and the speed of response, that is also controllable. The things I just mentioned here. So one convenient method of controlling the width of the depletion region is to build a pin photodetector. The eye region need not be truly intrinsic as long as the resistivity is high. It may have, the eye layer may have very light doping, but the thing is the eye layer has to have higher resistivity than p type, p layer and n layer. That is the main thing. So when that happens, most of the voltage appears across this eye layer. So electric field appears across this depletion layer, large electric field. So the eye region, okay. When this device is reverse biased, the applied voltage appears almost entirely across the eye region. If the carrier lifetime within this eye region is long compared with the drift time, most of the photo-generated carriers will be collected by N and P region. So since this is a eye layer, carrier concentration here is smaller. So lifetime may be larger. So if lifetime is larger, then most of the generated carriers can go to these contacts and can contribute to the current. So current may be large. Remember, we want more current from more is the current, more is the sensitivity. So this is how pin photodetector works. Another photodetector is avalanche photodetector. Here actually the figure is not shown. There are 4 layers. Pin photodetector has 3 layers. Avalanche has 4 layers. What happens in avalanche photodetector is in the depletion layer, the electric field is high enough so that the carriers which are drifting through the photo generated carriers which are drifting through the depletion layer, they can get high enough acceleration to cause ionizing collision. So when there is ionizing collision, there is carrier multiplication. Remember the effect, avalanche breakdown effect. There is carrier multiplication and there is current gain. So even a small number of carriers, photo-generated carriers, can create large number of uh, total carriers through this avalanche multiplication, and the total current may be large. So this is useful for detecting very low level of optical signals. Okay, so it is, if low level of optical signals are to be detected, it is often desirable to operate the photodiode in the avalanche region of the characteristics. In this mode, each photogenerated carrier results in a significant change in the current because of avalanche multiplication leading to gain. Gain means current gain. So this is how avalanche photodiode or photodetector works. There is actually another type of photodetector, MSM photodetector, metal semiconductor metal photodetector, which is not mentioned here. So I will stick to these two only.
Sir,
Yes.
you can repeat a bit about avalanche photodetector just once.
Here the avalanche process is used, avalanche breakdown process is used to amplify the current. So now level of optical signal is low, so number of photo generated carriers EHPs is small. So within the depletion layer, it's not shown, again the figure is not shown here. Within the depletion layer of a avalanche photodetector, there is large electric field. So when there is large electric field, what happens to the carriers, optically generated carriers? They will drift through the depletion region, right? When they are drifting, remember there is acceleration.
Yes, sir.
Now, acceleration means what? The carriers are gaining energy
Yes, sir.
because of the field present in the depletion layer. Now, there the field is so high that the acceleration is also very high. Electrons, those optically generated carriers, get sufficient energy to cause impact ionization. You remember impact ionization? The electrons collide with lattice atoms and create more electrons and ions. Okay,
Sir.
so that's how the number of electrons and holes generated increases through impact ionization. It is same as the avalanche process, avalanche breakdown process. So there is one, say for example, one electron generated generated by optical absorption, but that electron can cause impact ionization and create another electron. So two electrons are generated. That's how current gain is obtained. Number of carriers increases. Okay.
Yes, sir.
So current increases. So even if the number of optically generated carriers is small, the current may be large. So this is useful to detect low level of optical signals. Okay.
Yes, sir.
So this is about avalanche photodetector and pin photodetector. So that's all about actually photodetector. Any question on photodetector? Any more question? No question. Okay. So another short topic I will cover today, which is light emitting diodes. So far, I have talked about PN junctions, which are actually reverse biased. Okay. Photodetectors are reverse biased. Why? I actually forgot to mention. First quadrant operation, forward biased photodiodes can also be used for photo detection, but there is a problem here. For forward bias, W is small, the depletion layer width is small. Okay, as I have shown you, larger W is good for sensitivity of the photo detector. That's why this third quadrant operation is used for photo detector. So solar cell and this photo detector, both case actually uh, kinds of, you can say, reverse bias. Actually this is not reverse bias, there no voltage is being applied. This is a reverse bias PN junction. But LED, light emitting diode, and laser, those are actually forward biased PN junctions. Okay. So LED is nothing but a forward bias PN junction made with direct band gap semiconductor. You remember direct band gap semiconductor, where direct recombination happens and photon can be radiative recombination happens, and photon can be obtained from those semiconductor. So that is how LED and laser works. But for laser, there are some additional considerations which I will discuss in the next class. LED is pretty simple, just forward bias PN junction made with direct band gap semiconductors. So when carriers are injected across a forward bias junction, the current is usually accounted for by recombination in the transition region and in the neutral region near the junction. So remember, in the junction, when I discussed chapter 5, minority carrier injection, I discussed a topic which is nothing but the current or carrier injection at forward biased case. So when the device is junction is forward biased, minority carriers are injected from P side to N side and N side to P side. And those minority carriers, if you remember, decay exponentially, right? From both sides. Why do they decay exponentially? Because those minority carriers, holes in N side, electrons in P side, they recombine. Okay. That's why their concentration decays exponentially. Now, when they recombine, they release energy. When minority carriers recombine, electrons actually, when no electrons also actually both. When they recombine, the energy is released. Now, in indirect band gap semiconductors, silicon, germanium, this released energy will be obtained as a heat to the lattice, because the recombination will be non-radiative recombination, right? In a semiconductor with an indirect band gap, such as silicon and germanium, the recombination releases heat to the lattice. But on the other hand, in the material characterized by direct recombination, considerable light may be given off from the junction under forward bias. So this effect, called injection electroluminescence, provides an important application of diode as generators of light. So these are just diodes made with direct band gap semiconductors, which you forward bias. There is minority carrier injection from both sides. Those minority carriers recombine, and if the recombination is radiative, you get light. As simple as that. Now for LED, the frequency or the color of the photon is governed by the band gap of the semiconductor as given by the Planck's relation h nu equal to Eg. So when the carriers recombine, electrons holes recombine, they give off energy which is equal to the band gap energy, right? Eg is Ec Ev Ec Ev. So when electron goes from conduction band to valence band, they releases energy which is equal to this Eg. So this energy is obtained as photon. So from Planck's relation, we know that h nu equal to Eg. So nu is the frequency. So frequency is determined by Eg, band gap of the semiconductor. So a very important metric of an LED is, oh sorry. So what is happening here? You can control the frequency. Frequency controls the color. You can control the frequency of the emitted light by choosing suitable semiconductor with suitable band gap. Okay, this Eg. So a nu equal to Eg by h. So you can, depending on your requirement, you can choose a particular material with particular Eg so that you get a particular nu or frequency or color. Now, a very important metric of an LED is the external quantum efficiency, eta external. So eta external is internal radiative efficiency into extraction efficiency. So this efficiency means actually how efficient the LED is in converting electrical energy into optical energy. Here, actually, you are doing the opposite thing of solar cell. You are converting electrical energy into optical energy. So how efficiently an LED can do that? That is the efficiency, external quantum efficiency. So that actually is a product of internal radiative efficiency and extraction efficiency. Internal radiative efficiency is within the material how many photons are being generated from the recombinations. That is a, this is a measure of that internal radiative efficiency. So internal radiative efficiency is a function of the quality of the material and the structure and the composition of the layer. So if the material is pure, if it's defect free, then internal efficiency will be larger. But if the material is defective, the internal efficiency will be smaller, because if there are defects in the material, again there are trap levels or defect levels within the forbidden gap, and those trap levels or defect levels, if you remember, trap carriers when the carriers want to recombine. So you will get defect mediated recombination or trap assisted recombination, which I discussed near the beginning of the semester. One non-radiative recombination process is trap assisted or defect mediated recombination. So if there are defects, there will be non-radiative recombination through those defect states and we will not get light. So defective material will reduce this internal radiative efficiency. This is one thing. So defects in the material will clearly lead to non-radiative recombination. However, even if the internal efficiency is high, not all the emitted photons are extracted from the LED. Okay, the emitted photons from an LED have a wide angular distribution. So this is a PN junction, this is P, this is N. So the photons are being generated here near the junction when recombination is happening, uh, and because of this recombination, photon is being produced. Now these photons have to escape the semiconductor and go to the surrounding air. So when they do that, you can see that there is a semiconductor air interface. There is a plane which the photons have to pass or cross. Where since photons will be generated in different directions, the generated photons will have many directions. That's why it is said that the LED, the emitted photons from the LED have a wide angular distribution. since they have wide angular distribution, it may happen that at the semiconductor air interface, the photons will have total internal reflection. So if there is total internal reflection, photons will come back to the semiconductor and they may get absorbed. An electron from the valence band may absorb the photon and go to conduction band. So that photon is lost. So that is a, a loss actually. So how can we prevent that loss? How can we make sure that the photons which are generated within the semiconductor, most of them can come out in the light? So that is the extraction efficiency. What is the percentage of photons that can be collected at the air, surrounding air, from the generated photons? So in order to increase this extraction efficiency, instead of planar surface, this kind of dome shaped surface is used so that this total internal reflection is minimized. Okay, I am sure you have seen this kind of dome shaped LEDs in the labs. So this is nothing new to you, but this is done purposely to reduce the total internal reflection and to increase the extraction efficiency. So if an LED has a planar surface, the photons incident on the semiconductor air interface at angles greater than the critical angle would undergo total internal reflection and ultimately be lost via absorption within the semiconductor. Hence, typically LEDs are made with dome-shaped encapsulation, which acts as a lens so that more of the photons can be extracted. The things I just mentioned. So this is about LED. Uh, about LED materials. What are the materials suitable for LED? This is a very small topic. At the beginning of the semester, I told you discussed about the types of semiconductors, where I talked about compound semiconductors. Actually, elemental semiconductors cannot be used as light emitting materials because they are indirect materials. But some compound, not all, some compound semiconductors, binary, ternary, and quaternary compound semiconductors have direct band gaps and they can be used as light emitting material. That means material for making LED. An example, this is an example, there are also other materials. An example is gallium arsenide phosphide. Okay, this gallium arsenide phosphide. Gallium is group 3 element, arsenic and phosphorus are group 5 elements. So you can see 1 minus x and x. This x determines the percentage of arsenic and phosphorus, group 5 elements. So if you vary the percentage of arsenic and phosphorus, the band gap varies, amount of band gap varies, and also the type of band gap, indirect, direct, that also varies. So if amount of band gap varies, you can see if EG varies, nu can also vary. So depending on your need, you can choose suitable percentage of arsenic and phosphorus to determine, to fix the band gap so that you can get a fixed frequency light. Okay, so red LED, blue, yellow LED, white LED, those LEDs you have seen, those are actually made with different types of composition or different types of compound semiconductors. So one example is here. If you vary x from 0 to 0.45, the material will remain direct band gap material. If x is greater than 0.45, the material will become indirect band gap. So x equal to 0 means what? If you put x equal to 0 here, this phosphorus becomes 0, so it will be gallium arsenide. The material will be gallium arsenide. Then if you increase x 0.1, 0.2, 0.3, if x becomes 1, then arsenic becomes 0, so that material becomes gallium phosphide. So in between we have varied proportion, percentage of arsenic in phosphorus, up to 0.45, that means gallium arsenic 0.55, phosphorus 0.45, that means 55% arsenic, 45% phosphorus. For that composition, up to that composition, from x equal to 0, the material remains direct, so it can be used as LED material, and the band gap is variable. Band gap varies with the composition. So it's shown here, X is 0, X is 1. So when X is 0, we have gallium arsenide. When X is 1, we have gallium phosphide. In between, we have gallium arsenide phosphide for different percentages. And you can see the energy varies. The band gap energy varies with variation of X. Beyond this value, the band gap becomes indirect, so it cannot be used as LED material. But within this uh, range of X, the material can be used as a LED material. An example is X equal to 0.4. When X equal to 0.4, the band gap is around 1.9 electron volt. Okay, and that corresponds to red light. Okay, where কোথায় গেল? Okay, the most common alloy composition used in red LED displays is X equal to 0.4. So X equal to 0.4 means gallium, then arsenic 60%, phosphorus 40%. This results in efficient radiative recombination, and the uh, emitted photons are in the red portion of the spectrum. So 1.9 Eg is 1.9 around. So this 1.9 divided by H corresponds to a frequency which is actually the frequency of a red light. Okay. So red LD can be made with this. So this is the discussion on light emitting materials. So that's all for today. Any question up to this?